All right, we're going to finish up with the material that we didn't get to last time, and then we'll get into the material that we need to cover today. So let's get started talking about alcohols. And alcohols can function as bases because why? Pardon? They have lone pairs. That's right. On the oxygen, we've got lone pairs. They can function as what type of base? Lewis base. And all nucleophiles are what? Lewis bases. But are all Lewis bases nucleophiles? No, right? So alcohols can function as Lewis bases because they have an oxygen atom that has a lone pair of electrons, okay? And so that means that alcohols, just like water, will react with strong acids. So for example, if you take the generic acid HA, this could be HCl, HBr, H2SO4, whatever the case may be, a strong acid, the alcohol will react with it. Help me push the arrows. Where do we start? Oxygen to hydrogen and the bond between hydrogen and its anion to the anion, right. So how does that look? What other reaction have we talked about that looks very similar to? An elimination? Dehydration? Think about substitution. What does that look like? It looks like an SN2 reaction. And an SN2 reaction is nothing more than a Lewis acid Lewis base reaction. Okay? And so you can see that it's very similar here. We don't call it a substitution reaction. It is just the reaction of an alcohol with a strong acid to protonate the alcohol. Okay? Which way does the equilibrium lie? Now, you can clearly tell by the arrows that are up there, but tell me why the equilibrium lies the way that it shows. Okay. Well, it will dissociate, but that doesn't explain the equilibrium in and of itself. So you've stated a true statement. What do we know? Do we favor the stronger acid or the weaker acid in a reaction? The weaker acid. So we're going from a strong acid to a weaker acid. And so we're going to favor the weaker acid pair. And so you can also think of it as going from a stronger base to a weaker base, right? So yeah, the equilibrium is going to lie to the right here. You don't need to know by how much. It's not particularly relevant for what we're doing in here. But again, getting that feel for where acid-base reactions lie. Okay? If we had used acetic acid, where would you think the reaction would lie? More toward the left, right? More toward the left, because acetic acid is a weaker acid, and you're going to favor that weaker acid, right? So we all know that hydroxide is not a good leaving group, but water is a good leaving group. We talked about that multiple times last semester, right? And now that I have a protonated alcohol or an oxonium ion, right, I have a reasonably good leaving group, and nucleophiles can react with these oxonium ions in SN2 and in SN1 type reactions, right? Here we're going to talk about it in terms of an SN2 reaction. So you can imagine the nucleophile then reacting, right, in a typical SN2 reaction where the nucleophile functions as, well, it's a Lewis base functioning as a nucleophile attacking the carbon, and water leaving as a leaving group, right? And you end up with a new nucleophile carbon bond, okay? So what we've done in this particular reaction is we have converted OH, which as hydroxide is a horrible leaving group. You simply put a proton on it, and now you have a good leaving group because we know water's a pretty good leaving group, right? So we're going from a stronger base, water is a weaker base. So again, the equilibrium is going to be shifted to the right, okay? Now, you can't just use any old nucleophile in this reaction because nucleophiles, being bases, will also react with the acid that's present. So there's only a limited range of nucleophiles that this really works with. And they're typically the nucleophiles that are in the halogen family, okay? So, for example, we can take an alcohol and convert it to an alkyl halide pretty easily using either the hydrogen halides HCl, HBr, HI. HF is not in that category. The phosphorus halides like PCl3, PBr3, we'll talk about those. And one of my favorite reagents, thionyl chloride. Okay, it's one of my favorite reagents. In our lab, we've got about 5 liters of it that we were able to salvage from other labs that were being shut down. And so when we want to convert something from an alcohol to an alkyl chloride, that's our go-to reagent because we just happen to have tons of it in the lab. But all of these will work very, very effectively, okay? So if we take butyl alcohol and we react it with HBr gas, dry HBr gas, we will get what? What will the product be? Okay, that's right. So we go from an OH to a alkyl bromide. What do we think the mechanism is? SN1 or SN2? SN2. If we take propyl alcohol and we use HCl, zinc chloride, and heat it up to reflux, what's the product going to be? Chloride, yeah. And this mixture of hydrogen chloride with zinc chloride is known as Lucas reagent. Okay? We'll talk a little bit about that in just a moment. What are we going to get in this particular reaction? Tert-butyl alcohol plus concentrated HCl at 25 degrees. The chloride. Is the mechanism SN1 or SN2?
No, sorry, one with carbocation.
That's right. This one's going to go through a carbocation. Why? That's right. So we're going to protonate the alcohol. This is bulky, so the nucleophile can't attack. The leaving group has to leave, generate the carbocation, and then we can get that chemistry to work really well. This reaction is so easy, nobody can mess it up. Okay? We have done this reaction multiple times in my lab to get tert-butyl chloride. You literally take the tert-butyl alcohol, which is typically a liquid if the room temperature is good enough, and you mix it with an equal volume of concentrated hydrochloric acid in a separatory funnel, and you shake it, and everything is miscible to start out with. Does that make sense? Why? I got an alcohol. Is that alcohol going to be soluble in water? Why? It is polar. But what about my 5-carbon rule? Does it satisfy my 5-carbon rule? It does. Okay? The product, however, is that going to be soluble in water? No. So how do I know when the reaction's over? I see 2 layers separate, and that's the beauty of the reaction. You literally put the mixture in a separatory funnel, shake it up, put it in a stand, and just come back when you see the 2 layers. You drain the layers, isolate the organic layer, and voila, you've got pure product. It's the easiest reaction in the world to do. Okay? Nobody has ever been able to mess that one up. Okay? So yeah, we were right. We're going to get butyl bromide. That's going to be an SN2 reaction. Notice you also have another set of reagents that you can use. You can use sodium bromide and H2SO4. What happens when you take sodium bromide and you mix it with H2SO4? What do you generate? Huh? Is it? Look up there at the top. Dry HBr gas. What happens when you mix sodium bromide and sulfuric acid? You get HBr. Okay? Now, it turns out you can buy HBr gas in a cylinder that's expensive, and then you have to do a bunch of piping, which is not fun. Or, yeah, so this is how we make it in my lab. We never buy the HBr gas directly. We take a flask, we put in a bunch of sodium bromide, then we take a syringe and we drip in sulfuric acid, and it will generate HBr gas and just have it go straight into the reaction flask that we need. So anytime you see a salt like sodium bromide and sulfuric acid, think about the HBr or whatever. So if you take sodium chloride and H2SO4, you actually generate HCl gas. If you take sodium bromide and H2SO4, you actually generate hydrogen bromide gas. Lucas reagent, we're going to get the propyl chloride, and again, you need to know that name. Why do we need the zinc here? We're going to talk about it in the next slide, but why do you think we need the zinc? It does. That's true. Yeah, what do we know about our trend in terms of being a nucleophile as we go down the family? It gets better, right? Chloride's right up there towards the top. It's not a particularly great nucleophile. You really need a carbocation for it to react with efficiently. We can't generate a carbocation, so what do? We make the leaving group better. Yeah, we make it a lot better leaving group. That's exactly right. And if, yeah.
What part that makes it such a good leaving group?
We're going to talk about it on the next slide. Yep, we're going to get to that. So acids typically catalyze these reactions quite well to convert an alcohol into an alkyl halide. So sulfuric acid is quite frequently used, like you saw with the sodium bromide. We know that carbocation rearrangements will occur, especially when we're talking about secondary and tertiary alcohols, because we can generate those carbocations, and they can rearrange to more stable carbocations. So for example, if we took our good friend here, 3,3-dimethyl-2-butanol, which we would make from the alkene using oxymercuration, demercuration, right? And we subjected it to, let's say, HCl, you wouldn't get the product that you would expect. You would not get simply the OH being substituted for or with a chlorine, okay? You undergo rearrangements because we have a carbocation. The reactivity order of alcohols in these reactions is tertiary is greater than secondary, greater than primary, but methanol is greater than primary. Can you explain that for me?
Because of how small it is. There's nothing like in the way for the SN2 to work.
Okay, so we're talking about SN2, right? Very good.
There's no long chain for it to worry about.
That's right. So if we think about the protonated alcohol, right, if a nucleophile has to come in here, right, it's going to have to deal with that bulky group, even though it's primary. This will still happen. But here, the nucleophile has nothing to get in its way, right? And so we see that a lot of people will look at methanol and say that's a primary alcohol. It's not. It's its own class in these reactions. A primary alcohol has to have a primary group attached to the carbon bearing the OH. Methanol only has hydrogens. Okay, so we're going to see methanol react faster than primary. Tertiary, these reactions are going to be carbocation based. Secondary, what are they going to be? It's the fuzzy area, right? You're going to have SN1. You can still have some SN2. You can probably end up with a mixture of mechanisms. And primary has to be SN2. Very good. Okay. Yes, sir.
So we're talking like what we're talking about just saying. So is there a difference between ethanol and propanol? Like they're primary, but is there like a reaction speed?
There is a difference, but it's slight.
But it's not enough to really.
It's not enough for us to really worry about. Now, if you start putting branch groups out there that make it a lot bigger, it starts to get slower. But ethanol versus propanol, reaction's going to be different, but not substantially different. Not enough to get you a Nobel Prize, okay? So the reaction of tert-butyl alcohol with concentrated HCl, we mentioned in the previous slides that this, of course, is an SN1 mechanism. The first step is going to be what? Protonate the alcohol. That's right. Anytime you take an alcohol and you place it into strong acid, protonate the alcohol is your first step. Okay? Lewis acid, Lewis-based reactions always occur really quick. Okay? And so now we have our protonated alcohol. We have a good leaving group, but we've got a poor electrophile, right? We can't just have our nucleophile come in and kick out the leaving group in an SN2 process. But since it's tertiary, we can actually have the leaving group leave, and we can generate the carbocation with the bad geometry that they use in this particular slide. Okay? It does not look like a T, right? What is the hybridization here? It's trigonal planar in shape, but what's the hybridization? It's sp2, right? So we've got a vacant p orbital, right? And now this can either react with water and go back to the starting material, or the carbocation can react with the chloride nucleophile. Chloride's a good enough nucleophile to react with a carbocation. This is a fast reaction, and you end up with the nucleophilic attack. Now, if I set this reaction up in a separatory funnel, notice this is all reversible. Yet the reaction goes to completion. Whose principle dictates that and why? So if I had Megan come in, set up a separatory funnel, and she put in an equal volume of tert-butanol and an equal volume of concentrated HCl, and she mixed it up, she would get that reaction to essentially go to completion, even though it's an equilibrium. Why? Whose principle? Le Chatelier's principle. Now, Le Chatelier's principle states what?
That if it's got more concentration on one, it won't be equal. It's going to go to equilibrium. More concentration on one side is going to go on to the end.
Okay, so what's happening here? She notices what as the reaction proceeds? We started off homogeneous, right? What happened as the reaction proceeds? We got two layers. So what does that happen when we get that second layer? What's happening? Are we losing starting material? We're removing the product. That's right, because the product's not soluble in water, so it's coming out of the reaction mixture, if you will, right? And so that's essentially removing it from the reaction, and that forces Le Chatelier's principle to shift the equilibrium to the right. So this is a perfectly reversible reaction, but because the product's not soluble in water, it drives the reaction to the right. So you can use physical property differences to drive reactions. We didn't have to distill it. We didn't have to add a drying agent. We just used the fact that these alkyl halides are not soluble in water, and Megan was able to drive a reaction to completion, isolate this from the separatory funnel, go on and do whatever else she needed to do with it. Okay? Now, in these reactions, because we go through a carbocation intermediate, there's always a competition between the SN1 reaction and the E1 reaction. So dehydration is always a competing reaction. Once we generate this, right, we get to the carbocation intermediate. Nothing new there, right? And if our nucleophile functions as a base, we end up getting an elimination product, but it can also have the nucleophile acting as, or the base acting as a nucleophile and giving us product, okay? Now, before we get into this, how do I favor this reaction over this reaction? What about the temperature? So if I want to favor the substitution, I keep it low. So just like when I set it up in a separatory funnel, I'm doing this at room temperature. That's fairly low temp. What would happen if we decided to boil it? I could favor the elimination, right? So that works pretty well. The dehydration reactions, typically if you want to favor dehydration, you can increase temperature, but you can also pick acids that don't have anions that are very nucleophilic. So for example, concentrated sulfuric acid is an excellent dehydrating acid, okay? Because the bisulfate anion is a very poor nucleophile. It's very stable. The chloride is less stable than the bisulfate anion, and so so there's some good acids that are really good for this type of dehydration. Concentrated sulfuric acid is the one that we almost always go to. What are other good dehydrating acids? Paratoluene sulfonic acid? The potassium one? Okay. So phosphoric acid. That's right. Concentrated phosphoric acid is good. Concentrated sulfuric acid is good. And paratoluene sulfonic acid is good. There are other good dehydrating agents that are out there, but I'm not going to hold you responsible for them. Okay? So if you want to favor the dehydration, increase the temperature and use one of these non-nucleophilic acids. If you want to favor the substitution, lower the temperature and use something like HBr, HCl, or HI. Okay? Now, the SN2 mechanism, let's look at methanol reacting with concentrated HBr. The first step in all of these reactions, alcohol, strong acid, protonate the alcohol, right? We now have the protonated alcohol. We've got a good leaving group, but can it leave? Why can't it leave? We can't have a methyl carbocation under these conditions. It's very hard to get a methyl carbocation. It's so hard to get a methyl carbocation that actually a Nobel Prize was awarded to George Olaf for being able to do it. He used what's known as a mixture of acids that they called magic acids. You got to love that term, right? But he was able to generate very unstable carbocations through this mixture of what are known as magic acids, which is beyond the scope of the class. Okay? Actually, George Olaf got a Nobel Prize for more than just making carbocations, but that was part of it. I mean, you know, when you tell a chemist or you tell anybody it's impossible to do that, we really want to test the limits to see what's possible. And so he spent a large part of his career doing that kind of stuff, trying to see where the limits and the bounds exist. And so, yeah, you can generate methyl carbocations, but it ain't easy, okay? Now we have the protonated methanol. We have a nucleophile. Bromide is a good nucleophile or a poor nucleophile? It's a good nucleophile, right? It's right here on the periodic table. As we go down the family, we know the nucleophilicity increases, and we get the SN2 reaction to occur, right? Just like you would expect, bromide comes in from the back, kicks out water as a good leaving group. You end up with the methyl bromide, and the reaction is over, okay? So if we think about this reaction, what do we know about methanol? High boiling point, low boiling point. Medium? That's a safe statement, isn't it? It's up there, yeah. It's less than water, but it's a liquid at room temperature, right? What about methyl bromide? At a substantially lower boiling point. Methyl bromide at room temperature is a gas. Even though it weighs more than methanol, it's a gas. Why is it a gas and methanol is a liquid?
Hydrogen bonding.
That's right. So we have hydrogen bonding here. We have no hydrogen bonding here. And so this is a liquid at room temperature. This is a gas at room temperature. And so as this reaction occurs, what do you expect to happen? You expect to see a gas come out, right? And in fact, methyl bromide is used as a fumigant in many countries to kill a variety of pests. Turns out it's not a particularly environmentally friendly fumigant, but in places that are mosquito-ridden, I mean, and more so than what we experience, it's still allowed for use as far as I can recall. And so it's limited, it's an ozone killer, but it does have its place. Okay. All right. We know that the reactivity of the hydrogen halides is as follows, that HCl is, the reaction occurs slower than with HBr than it does with HI. So as we go down the family, the rate of reaction is going to increase. Explain that for me. Explain why if I take an alcohol and I react it with HCl, it's going to be slower than if I react it with HBr than if I react it with HI. Let's just say a primary alcohol. That's right. Why is it the nucleophilicity and not the acidity? Because acidity goes down as we go down a family. Why is it not the protonation step that's the slow step? Hmm? Well, I'm just saying if we use these. Okay. They're all strong acids, right? And we're going to, in all cases, we're going to get that weaker acid, that protonated alcohol, right? So the equilibrium is going to lie to the right in all three cases. So that's not the rate determining step. That happens pretty quick. It's got a low energy barrier. But the SN2 part, the nucleophile has to come in, interact with some stuff, and the leaving group has to leave, and that's slower. And so the better the nucleophile, the faster the reaction, right? And in fact, chloride is such a poor nucleophile that the reaction of primary alcohols with HCl, it will occur, but you're going to be around for a long time. And so to speed it up, you add zinc chloride, okay? And when you have a mixture of zinc chloride and HCl in water, you call that Lucas reagent. And so what happens is zinc chloride is a Lewis acid. It can make a complex with oxygen. And so Our Lewis base, the alcohol, reacts with the zinc chloride, makes this intermediate, which is actually a better leaving group than the protonated alcohol. Okay? The chloride can then come in. This bond is now weaker than usual, and this can leave, and you end up with the SN2 product. Plus, you end up with zinc-oxygen bonds. What do you all know about zinc-oxygen bonds? Are they strong or are they weak? What do you know about zinc oxide? It's the stuff you put on your nose. It's white, right, when you go to the beach. What do you know about it? Is it stable? Is it unstable? It's very stable. I mean, if you buy that stuff, you can keep it around forever as long as it doesn't dry out, and you can smear it all over your face, and it works really well, right? Zinc-oxygen bonds are actually quite strong. And so that's the driving force here, is that we've generated this very strong zinc-oxygen bond, which in effect weakens this carbon-oxygen bond, and therefore the nucleophile chloride can attack, and the reaction can go a lot quicker, okay? And so there's actually a test that I think you all do this semester, I can't remember, where you use Lucas reagent, or maybe you did it. You haven't done it yet? Okay, so where you use some Lucas reagent to detect whether or not you have different types of alcohols. Okay, so let's do a quick concept test. Get with your partners. Let's spend 3 or 4 minutes. Draw all possible products. You're all by yourself this semester. It's tertiary. Remember, it's going to flatten out, though, right? So this will actually be kind of coming out this way because it's going to have to be planar, your carbocation. So don't draw it like that. But it's tertiary, so it's okay. All right. What's going to happen in the first reaction? What are we going to get? SN2, but what's the product going to be? Name it for me. Yep, 1-bromopropane. Yep, that's what we're going to get, right? And it is an SN2 reaction. How about the second reaction? 2-chloromethane. Ethane? How many carbons are up there? There you go, yeah. 2-chloropropane. So we just took household rubbing alcohol, and we took concentrated HCl, which you can buy at Lowe's. Well, almost concentrated. It's called muriatic acid, which is actually a diluted version. You use it to clean brick. And we went to the grocery store and bought some, actually you can buy zinc chloride at the pharmacy, okay? Mixed all this stuff together and you just made 2-chloropropane in your kitchen. Not that that's particularly useful.
So if we mix the rubbing alcohol and the concentrated HCl together, it should be miscible. What will happen?
It would actually react, but very slowly.
Okay.
Yeah.
That's right.
Add the zinc chloride and it'll go a lot faster. Okay? How about for the third one?
That's going to have 2 answers.
We're going to have 2 answers. We're going to have the chloride how? We can have it axial or equatorial, right? And so we know our big group is always going to want to be equatorial, and so we can have chlorine that is axial and we can have chlorine that is equatorial. What I want you to think about this weekend, okay, and be prepared to answer on Monday on a note card. I'll bring note cards, okay? Which one of these would you predict to be the major product and why? I have not given ratios here, and I don't expect you to give me 10 to 9, whatever. I expect you to tell me which one of those you expect to be the major product and why. So think about transition states. Think about the carbocation and how the nucleophile would attack, and that'll give you your answer, okay? But that's kind of a weekend assignment. Think about which of those 2 products would you expect to be the major product, okay? We can also form alkyl halides from alcohols using other reagents like the phosphorus reagents and thionyl chloride. The most common phosphorus reagent that we use in organic chemistry for this purpose is PBr3, okay, phosphorus tribromide. Now, what happens is we can take an alcohol, 3 moles of one alcohol, in this particular case 2-butanol, and 1 mole of phosphorus tribromide, and we're going to get 3 moles of the alkyl halide, 2-bromobutane, and a mole of H3PO3, or phosphorus acid, okay? So notice the ratio, 3 to 1. That's kind of convenient, right? We don't need a whole lot of PBr3. We only need 1/3 of it, okay? What do you know about the phosphorus-oxygen bonds in terms of their strength? How do you know that? Biology, right? What holds DNA together? Phosphate backbone. You think Mother Nature's going to pick molecules to hold your genetic information together that's weak? No, we'd go through all kinds of mutations all the time, not particularly stable, right? And so bringing in a little biology, what you know intuitively from biology, because you know that genetic information is stable, it's held together by a phosphate backbone, intuitively you should know that the phosphorus-oxygen bond has to be strong, right? And so this is the driving force for this reaction. This reaction is extremely exothermic. It lies to the right. When you take an alcohol and you add PBr3, if you're not careful, it overboils on you and pops out of the flask. You have to be very careful when you do this reaction. You have to cool the alcohol down to below 0 degrees, and you have to add the PBr3, usually very slowly, to help dissipate the heat. I had a student do this reaction once. It got out of hand. It went up through the condenser, up into the hood, all over the place. It can be a very, very vigorous reaction, to say the least. They did. They took 10 milliliters of PBr3 and it almost immediately, okay? You can also take an alcohol, react it with thionyl chloride, which again is one of my favorite reagents because it makes for a very nice cleanup, and you end up generating alkyl chlorides very, very conveniently. The nice thing that I like about this reaction are the other byproducts or gases. So as I'm doing this reaction in the hood, sulfur dioxide blows out the top of my condenser, and I don't care about it. HCl also blows out the top of my condenser. I do care about that one because it starts to corrode my hood. So I actually feed this through a bubbler that contains sodium hydroxide, so the HCl reacts with the sodium hydroxide, and you don't have that gas just blowing out. But nonetheless, this is very, very easy to do. and the byproducts, again, are very easy to get rid of. They're gases. Okay? Notice this is typically a 1-to-1 ratio. Okay? So let's look at the mechanism. This is the Lewis structure for thionyl chloride. The alcohol, the oxygen, acts as a Lewis what? Acts as a Lewis base, acts as a nucleophile, attacks the sulfur. The chloride leaves. We now end up with a sulfur-oxygen bond. Typically, you run these reactions in the presence of a base, although it's not absolutely necessary. And so a lot of people will run these with pyridine as the base. Pyridine then deprotonates the protonated alcohol, and you end up with this, which is, now this is our good leaving group. Now the chloride can come in, attack the carbon. This leaves as sulfur dioxide, and you get chloride that leaves as a leaving group as well. Okay? You don't have to add the pyridine. It just basically functions to soak up HCl. If you look at it overall, this is a pyridinium ion with chloride. That's like reacting pyridine with HCl. Okay? And so you don't have that HCl gas blowing out the top of the condenser. But then I got to clean this up. So I usually don't do this. I just run the gas through a scrubber, because thionyl chloride alone will promote this reaction with no problem. Chloride is a strong enough base to deprotonate this protonated alcohol. Okay? Pretty simple mechanism. Phosphorus tribromide is fairly similar. The oxygen reacts with the phosphorus. We know we've got a strong phosphorus-oxygen bond. One of the bromides leaves. You end up with this molecule. You've got a good leaving group. The bromide now comes in and attacks the carbon. The leaving group leaves. You end up with this. This still has a phosphorus and bromine bonds, so it can go in and continue to react with more alcohol. They've just only shown you one step here. So this can then actually come up and react with more alcohol until you've reacted all of the phosphorus bromide bonds. Okay? So that's a fairly straightforward mechanism as well, where now we basically, in all of these cases, what are we doing? We're converting the alcohol into a good leaving group. So anytime you can think of turning an alcohol into a good leaving group, the mechanism is going to be fairly similar to this. Okay? So the overall thing that you need to know in terms of reagents, if you want to convert an alcohol to an alkyl chloride, you've got two reagents that you can use. You can use HCl, or you can use thionyl chloride, right? You know that you can use HCl also in the presence of zinc chloride if it's a primary alcohol, right? So it's useful for all alcohols. It's an SN1 mechanism for secondary and tertiary alcohols, and it is an SN2 mechanism for methanol and primary alcohols. And it's this situation right here where you'd want to add zinc chloride. You'd want to use Lucas reagent. Thionyl chloride works really well for everything but tertiary alcohols, because again the chloride has to come in an SN2 type mechanism, and so it will work very well for these, but not so much for your tertiary alcohols. If you want to convert an alcohol to an alkyl bromide, here are your reagents that you need for that. You can use HBr. Works for primary methanols, secondary, tertiary. The mechanisms are going to be slightly different. Not slightly, quite a bit different, right? For primary and methanol, you got SN2. Notice we don't have to add zinc to this reaction because bromide's a pretty good nucleophile. And PBr3 works really well for methanol primary and secondary because it is an SN2 mechanism regardless of the alcohol type. We can also convert alcohols into alkyl iodides if you use HI. Practically, though, most organic chemists don't do this because HI is very expensive. It's a lot more expensive than buying HBr or HCl or even thionyl chloride. So usually we try to get away with making alkyl chlorides or alkyl bromides. But if you need to make an alkyl iodide, you can use HI, bite the bullet, pay the price for it, and you can get the product that you need there as well. Notice what's absent. Fluorine's absent. That's right. So if you take an alcohol and well, this one doesn't go boom. But if you take an alcohol and you react it with HF, the reaction doesn't really work very well. Can anybody tell me why? Okay, it is a bad nucleophile, but what else? Is HF a strong acid or a weak acid? It's a weak acid. So if I take HF and I mix it with an alcohol, am I going to get a lot of the protonated alcohol? No. So not only is it a poor nucleophile in water, it doesn't really protonate the alcohol very much. Okay? Now, again, we want to remember that not all the acids in the halogen family are of equal strength, right? And HF is weak. It's about the same acidity, more or less, as acetic acid, okay? Except you wouldn't want to drink it because it does destroy tissues. Yes?
Does PBr3 go faster than ABr3?
My experience has been that PBr3 is extraordinarily exothermic because of the strength of that phosphorus-oxygen bond. And so the reaction does occur very, very quickly. Could I tell you right off the top of my head what the rate difference is? I can't. But it's quick. It is. You're making the leaving group extremely good because those phosphorus-oxygen bonds want to be formed. Okay? You can also make the alcohol into a leaving group by what's called tosylating the alcohol. Okay? So you can convert the OH into a tosyl group or a tosylate. Okay? Notice this oxygen is the oxygen from the alcohol, and all of this comes from a molecule known as tosyl chloride. Okay? And this is a pretty good leaving group. The other ones that they talk about in the book are called mesylates, where you have the same thing here, except instead of this aromatic ring, you just have a methyl group. And triflates, which is essentially the same thing, except having this, you just have a CF3. All of these make very good leaving groups. They're very easy to make, okay? And in fact, in labs, sometimes we have to make tosyl groups or mesyl groups or triflates to do the chemistry that we want on an alcohol. We know that the alcohols are poor leaving group, but the tosylate, the mesylate, and the triflate are all very good leaving groups. Okay? The mechanism for this is quite simple. The alcohol reacts with the sulfur. The sulfur has a chlorine on it. This is called tosyl chloride. Leaving group leaves. You end up making the protonated tosyl group. You have a base. Usually they use pyridine. Comes in and abstracts the hydrogen, and you end up with the tosylated alcohol. Notice we start with the S configuration. What do we end up with? The S. So I just took an expensive starting material and I preserved its stereochemistry. Now I have a leaving group that has the S stereochemistry. What would have happened if I had taken this and I reacted it with HCl to try to make the chlorine my leaving group? Would it have completely swapped? Or racemic, right? And so I just took a very expensive starting material and made it a very cheap product. Your business will go bankrupt and you will get fired, right? Yes, that's why we do this. That's a good point. That's where this is heading. Yeah.
And this one, is the chlorine strong enough to take the deprotonate the alcohol?
It is. It is strong enough, but typically people add pyridine so that you don't have the HCl to deal with. So even in our lab, when we do this, we typically take the tosyl chloride in a mixture of pyridine. Sometimes you can use pyridine as the solvent, and then you add the alcohol, and it works really, really well. This reaction, hard to mess up. Okay. So now you have a tosylate. That tosylate can function as a leaving group. So we can take, this is ethyl tosylate. We've got a strong nucleophile here as methoxide. We do an SN2 reaction. We just made an ether. This is not technically the Williamson ether synthesis, but it's very similar, right? The Williamson ether synthesis would be between an alkoxide and an alkyl halide. Tosylates react very similarly to bromine. They're about as good a leaving group as bromine, somewhere in that ballpark. So anytime you see OTS, think of it as a leaving group. Don't let that get you confused by any stretch of the imagination, right? So we can do SN2 chemistry. We can do E2 chemistry through eliminations, all that stuff that we've already talked about, right? And so let's look at this example. I don't want you to work on this one because we're running out of time. But this is not tosyl chloride, this is mesyl chloride. Notice we just got the methyl group here. Doesn't matter, okay? We take this, pyridine or whatever is our base, react this together. What are we going to get in this box?
Same thing as that, just with the
And now we have a good leaving group. Turns out that a mesyl leaving group is slightly better than a tosyl. Okay? So we've got a pretty good leaving group. Now I take this and I react it with CH3S Na. What's going to happen? It is a nucleophile. What's nucleophilic about it?
That's sulfur.
That's right. What do we know about sulfur with a negative charge? What kind of nucleophile is it?
Is that like a super?
It's a supernucleophile, right? So what's going to happen? We're going to do an SN2 reaction. It's secondary. I can do SN1 or I can do SN2. Why does this one favor SN2? Because the leaving group's really, really good, and the nucleophile is really, really good, right? Would I do this in a polar protic or a polar aprotic solvent? Polar aprotic. And we end up with the product where we completely inverted the stereochemistry. So we started off with one stereochemistry, and we inverted it completely. So that's good, if that's the stereochemistry that you want. Okay?
That would be racemic.
That's not racemic. No, if you start off with S, you get R. If you start off with R, you get S. It is completely inverted. All right, we're kind of at the end for today. I'm going to stop here. Work on that this weekend. I'm also going to post a brief thing to YouTube about our inverted lecture on Monday. So view the pencast. It's pretty short, but I'm also going to post something tomorrow on YouTube. So look at your remind for when I get that posted. And don't forget the YouTube channel. It's there to help you. Have a good weekend.